Welcome back, students. In this video, we are going to start with the mirror equation. This is something that you have come across already in your 10th standard, but this time we will do it a little more rigorously. We will try to iron out some of the wrinkles in your understanding of these diagrams, the object image diagrams, the ray diagrams as they are called. And I want to give you an understanding of all this, which you may not have understood so well when you studied the same things in your 10th standard. So that is what we will do now. I have a concave mirror here. It's a concave mirror. Okay. Notice that when you look at it like this is not that bent. You see, it's almost like a straight line, but it's actually a concave mirror. So this is critical. This is what I said when I talked about cutting mirrors out of spheres. You see, this is barely perceptible. This curvature is barely perceptible. It's almost straight line. But actually this is a part of a big sphere. Okay? So, since this curvature is very small, all the lines, all the rays that fall on this, there is this axis, the central axis that goes through the center of this mirror. All the rays that fall on this, like the parallel here, parallel to the central axis. All these rays, like this thick beam, okay, all of them would behave like paraxial lines. Because you can see that the curvature is barely visible. It is not like this, or it is not like this. It's barely visible. Okay, it's very slight curvature, which tells you that this must be part of a very big sphere. Okay, so I want you to understand this. So this is where the paraxial lines become very important. Now if the curvature is too big, like if it curves too much, then clearly you can only take a few lines, or very small, a thin beam as paraxial lines. But since the curvature is very small, and you see it is very slowly changing, this curvature, all the lines that are almost parallel to the central axis can be treated as paraxial lines. So the beam of paraxial lines is much bigger in this case. That's important. So the equations that we derive with paraxial lines will be applicable for the whole mirror. I want you to understand this. Well, if I draw, like if we were to find the distance, from maybe this point to the center, that is not going to be different from this point and this. Notice it? You see, it's almost the same. Maybe a millimeter difference, but it's almost the same. So when I take 20 centimeters and 30 centimeters and 50 centimeters, the distance between this point and this point is the same as that point, parallel, like the point is above it, and the top of the mirror, because the mirror is almost straight, almost plane. I want you to understand that part. Okay. Second, I will be drawing the diagram with the mirror like this. Okay. The mirror is going to be kept like this, and I'll keep an object here, and that object will make an image somewhere, right? So I'll be drawing only one line or a second line here. So does it mean that there are only one line or two lines only, or going from that object? No, that is not true. Because if I take a point, for example, if I take the tip of this, pen. I can see the tip, and you can see the tip, which is the camera can see the tip, and somebody who is sitting there can also see the tip, and a person who is sitting there will be able to see the tip, and the person who is sitting here will also be able to see the tip, and here will be able to see the tip, and the person who is sitting right behind me will not be able to see the tip because I will be blocking the ray that is going from the tip. So what I mean by that is, when you have an object, light travels in all directions. So there is a ray there, there is a ray here, there is a ray there, and there, everywhere, and there, ray there. If somebody is going to sit there, then that person also will be able to see it. From the very top, you can see it. How am I able to see the tip from this point? Like this. How am I able to see it? Because light from here goes up too. So it travels in all directions, three-dimensionally. So you can imagine from any object, rays which emanate from that object and travel in 3 dimensions. So when I talk about a ray, I may take a single ray. Which ray would I take? I would take the ray which reaches my eye. That's the ray I will take. The ray that reaches the camera doesn't reach me. I can't see that. But you see, what I can do is I can keep a mirror like this and then block that ray which is going to go to the camera and redirect it to my eyes. Now I can see the tip. I can see the tip here, and I can also see the tip in the mirror. Why? Because I have blocked the ray that was going to you and redirected it towards my eyes. So I blocked it, redirected to my eyes. So what I can see are the rays that reach my eyes. Even though the rays go in all different directions, what I can see is the ray that is reaching my eyes from here. And that is true for all objects. I am able to see the camera in front of me because the rays from the lens reach my eyes. So I can see. I can see the chair here. I can see the table there. I can see the shelf there. I can see the cups there. I can see all of them because the rays from those objects reach my eyes. If the rays don't reach my eyes, I can't see. So for you to see anything, 2 things must happen. 1, you must have the receiver, the eyes. Then the rays must reach your eyes. I may have this pen in the dark, in the night. There's no light. And if I look at it in the dark, I can't see it. I have my receiver, but I don't have the light coming from here reaching my eyes. And that is why you are not able to see objects in the dark. You are not able to see objects in the dark because the rays from the object do not reach your eyes. So you need 2 things, the apparatus, the receiver, and also the rays that reach your eyes. Without these 2 things, you can't see anything. I can't put out my arm outside and then see the wall. I can't see it. Okay, I can't see anything through my hand. So this is not the receiver for that. This is not the receiver for visible light. But I have to go out and see. Maybe if I put out my neck and then bend, then I'll be able to see the wall of this room. So light and also the apparatus, both are required for you to see things. Okay. And the other point is that if you have an object, if you have a point object, then light goes in all different directions. And we are concerned only about a few rays, particularly the rays which reach our eyes. Okay. So I want you to keep this in mind. Second, And you may have seen that in all these drawings, you may have seen only one ray or two rays. So does it mean that there are only one ray that which reaches here? No. If I take this tip and we keep the object here, the rays are going in all directions, three-dimensionally, they go. Okay? Then a ray from this tip will hit here, hit here, hit here, hit here, everywhere. The bunch will hit here. But then I would be interested only in one or two rays, because I know that all of them, all these rays, the bunch of rays from one tip, one point, will obey the law of reflection and converge at one particular point. We'll do it now. Let me try to explain that to you in the diagram. Okay, this is my mirror, and this is the axis. And let us suppose that I have an object like this. Generally, you see that there are only two rays drawn for these things. But does it mean that only those two rays are traveling from the tip? No. Rays from the tip are traveling in all directions. Ray from here is coming to me because I am able to see the tip. Ray from there is going to the camera because you are able to see it now. That tip. Why are you able to see it? Because the ray goes there. So the ray comes here and then the ray goes there too, to the lens. I am interested in the rays that go to the mirror. Okay. So let's see. Okay, now the other thing that I want to talk about is this. Let's say, so there will be a ray like that, there will be a ray like that, a ray like that, a ray like that, a ray like that, and there will be a ray here too, but that will miss the mirror. Okay, that will miss the mirror and then keep traveling. And we are not bothered about that now because we are going to study what will this mirror do with the rays that fall on the mirror. Okay, so that is what we are interested in. So all these rays will fall on this. I mean many more, and all the rays in between. All of them will fall from one tip, from one point. But at every place, at every point on the mirror, they will undergo the law of reflection. I must be equal to R. The angle of incidence must be equal to the angle of reflection. Okay? And at every point, you have to draw a normal. Okay? That will go through the center of this sphere. Okay? The sphere from which you have cut this mirror. So, if I take this mirror, if we take a point, it is not that the rays will hit here, 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 here. No, you can see that. The rays will come here and then hit here too. And then here, 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 here. So the whole mirror is going to be filled with rays from just that one point. Okay? I want you to understand that. It's not just it's not a point-to-point mapping. From one point, you will have rays hitting this mirror on the entire surface. Because there is a beam coming out, there is a cone of light. It's a cone of light coming from the tip. And all of them will fall on this mirror. And all of them will undergo the law of reflection. And all of them will make an angle with their respective normals. At every point you will have a normal. And with that normal, all of them will make an angle. And all of them, as I said, will undergo or obey the law of reflection. And all of them will come and focus, converge at one point because of the spherical nature of it. If it is not spherical, then it wouldn't. Okay? But since it is spherical, then you can expect it to converge at the point. Okay? So, this is for one. So, law of reflection will be obeyed here, 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 everywhere it will be opaque. So you can see that that can even be a parallel line like that. Okay, but even if it is parallel, then the law of reflection will be obeyed there, and in the line we know that it will go through the focal length. We proved it yesterday. In the previous video we proved that. So I want you to understand that first. I want you to understand that. So at every point the law of reflection will be obeyed. So this will be reflected maybe like this, and then this will be reflected like that, this will be reflected like that, and this will be reflected like that, this like that, and this like that. So all of them will focus here. So this one point will make a corresponding point here. But notice here, is there only one point on the object? No, you have all the other points. You see, it's not just a chip, there is something else too. Let's say, let me take this one. Let me take this point, maybe here. What will this do? Again, it will do what the first point did. It will be sending out rays in all directions. So you can say that this will also be sending like that, and like that, like that, and like that. Miss there. And then all of them again will converge somewhere, somewhere, like that. Okay, you can see that you're getting a second point here. For this point you get this image. So like this, there would be a maze. There will be lots and lots of rays going and hitting the mirror and then coming back, getting reflected, and then they'll come and focus and join. They'll do this. It's every point will do that. Every point will have this thing. But what we generally do is that we take the top and then we take the bottom. And what will the bottom do? The bottom will also do the same thing, and it's a different color. This point, let me take this point, because if I take an object, then it will have a bottom point also, right? So this will also do the same thing, like this, like this, like this, like this, 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 and then get reflected there, and there, 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 something like this. So third point, the bottom will make this. So what is understandable is, if this tip makes the image here, and if this tip makes the image here, if this point makes the image here, and then if this point makes the image here, then every other point in between must be making their respective images between these 2 points. Okay? Because you start with the top, and for the top you get a point, and you then end with the bottom. For the bottom you get this point, and every other point would lie between the top and the bottom. Okay? So actually this is what is happening. You see how messy this is? From each point, millions of rays go from each point, and then they go hit the mirror. You generally draw 2-3 lines, but that is not the story. From each point, a set of beams, a set of rays hit you, the entire mirror, and then from another point, another set of rays hit the mirror. Then another point, another set of rays hit you. And from each point, a million rays. And there are millions of points, infinite number of points, theoretically speaking, between the top and the bottom. Then they all hit you. So it's a mess. It's a total mess. Then they get reflected, and then they get focused at a particular point. Okay? This will make an image at one point, and another point will make an image near it. The third point will make an image near that, and then they together become one full image. Okay? So this is what is happening. this is a mess you are right now seeing. But this is not how we draw this picture. Why? Because all I need is this point and this point. If I know where this point is going to make its image, and if I know where this point is going to make its image, I know that all the other points will make their images here, between these 2 points. 1. Second, to find these points, for example, take this point, the top point making here. Okay, to find these points, I don't need so many rays, because I know each ray will pass through the point after reflection. So if we take this ray, the ray goes there, if it gets reflected, goes through the point. And then if we take another ray, it goes reflected, it goes to get reflected from the mirror, and then goes through that point. Okay. So every of the millions of rays, all those rays will go through this point. So I don't need all these lines. If I just have 2, then I can find this point. The intersection of these 2 will be that point. Meaning, all the other rays from that object point will go through this. I don't need all of them. I just need to know where they will go through. I don't need to know all these rays. I just need to know where, at which point all of them will go through. And to know that, 2 rays are enough for me. I don't need more than that. I want you to understand this. Likewise, for this point again, I figure out where the other, where all the rays from this point will go through. And if I can figure, for that too, I will require two rays, nothing more than that. If I get them, then I found the top point and the bottom point. Now every other point must be lying between the top and the bottom. If I get a reflection on the mirror, then if my head is here and my feet is there, then my mouth must be somewhere in between, right? It can't go somewhere else. It has to be between those 2 points. So when I draw a ray diagram, I simplify all this mess. But you have to understand that what is happening actually is a mess for human conception. From every point, millions of rays. And all these millions of rays obey law of reflection. And for a point, you will have another corresponding point after reflection where all these rays will converge. In this case, in a spherical mirror. So for every point, you have all these converging points. And how to identify them? Simply. To identify them simply, I don't need all the millions of rays which emanate from that one point. I need just 2 of them. Any 2 is fine. Any 2 is fine. I can take this ray, I can take, for example, this ray, and I can take this ray, and then those 2, if we apply law of reflection and find out where they intersect, then I know that point. Any 2. You don't have to take the parallel ray. There is no rule, there is no hard and fast rule that says take the parallel ray. Okay, and then take another ray which goes through the focal point, the focal length of the mirror, focal point of the mirror. No, there is no such thing. There is no hard and fast rule. You can take any ray at any angle. Just apply the law of reflection to those rays and find out where they meet. 2 of them are enough. Because if you identify the point, you know all the other millions of rays will have to go through that point. Okay? I want you to understand this. It is actually a mess like this. It's a 3-dimensional mesh. Here I have drawn it in 2 dimensions, but actually it's a 3-dimensional mess. Okay, it comes and hits everywhere and does this. Okay, so point start. If you have a point, it hits here, not just in a straight line, up and down. It also hits here, and it hits here. But all these points, all these rays, from all these points, the rays will go and converge at one point. Okay? I don't need all these millions of rays. Just two are enough for me to identify that point. If I identify that point, I know all the other rays from the object point will converge there after reflection. Hope this is clear to you. So before we do the mirror equation, I want to give you a list of rays, 2-3 rays, which you can use very easily to draw the ray diagram. Okay? I mean, as I said, like you can take any two rays. It doesn't matter. You can take any from a particular point on the object. You have an object and you take any particular point on the object, and from that point you can draw any two rays which go and get reflected from the mirror, and find the point of intersection, and that is the image point for this object point. Any two rays. Okay? But the only trouble you would have in adopting this approach is you need a protractor, you need to measure the angle, you need to draw the normal, and you need to find the angle of incidence, and for the angle of incidence you need to draw the reflected ray at the angle of reflection. Okay, all that you need to do. So in order to avoid using a protractor and using too much of geometry, we'll go with some simple rays. These rays will do this all the time. So take them, and then you don't have to worry too much about the angle. Okay, so that is important. I just want you to talk about them first. The first rule is you can take any two rays. Okay, any two rays. Enough. Okay, any two rays. And take them. You need to find the point of intersection after reflection. That's all. And any two rays. But then they need to obey the law of reflection. The law of reflection. They obey law of reflection, meaning I, angle of incidence, is equal to angle of reflection. So then you don't have to worry about anything else. You don't have to worry about parallel rays, you don't have to worry about rays that go through the focal point, or all those things. You don't even need to worry. This is the most general approach. But then there are some specific rays that you can make use of. First one, the ray parallel to the axis. Okay, I'm going to draw the picture here. So if I have a mirror like this, and then this is the object, and then I take this point, then this ray is going to be parallel to the axis, parallel to this axis. Then after reflection, this ray will go through the focal point of the lens. So this is F, and this is going to be C, where C is the center of the sphere, the spherical mirror. Okay, so this will go through. Okay, this we saw. Ray parallel to the axis will go through the focal point. That it's an easy ray to pick for any object. Okay. Third, the ray that goes through the focal point focal point will be parallel to the axis. This is the axis. Then if the ray goes through the focal point, then that will be parallel. Okay? So there are many rays. I told you millions of rays are going from this point. I have taken one ray, and my next ray would be this. Okay? There are many other rays from that point. I'm not bothered about that. I'm just talking about this. So this will go and this will be parallel. Okay? So this will be parallel to the axis. Now you see you got two rays, and now you have found the point of intersection. From this ray it was coming like this, and from this ray it's coming like this. So this is actually the point of intersection. That's the point of intersection. So you know all the other rays will have to go through that point because it's a spherical mirror. All the other rays which hit this mirror will have to go through this point because of the spherical shape. So you found it. I don't need to draw any other ray. Okay, so this is another easy ray that you can make use of. Now, if you use these two rays, you don't need a protractor. You don't need to measure the angle. I told you can take any two rays. Here, if I use these two rays, I don't need a protractor. I don't need to measure the angle. Just draw the line. Done. I'm done. Okay, so that's what it is. So this is also another easy ray. And what is the fourth easy ray? The fourth easy ray is the ray that goes through the center of the sphere, the spherical mirror. See, and that will get reflected back. That's obvious, right? Because you see, suppose I take this. This may not be possible all the time. Okay, this may not be possible all the time. Because if I take this mirror and if I take an object here, the object is 0. You see, I'm going to draw a big sphere, right? And this line, if you think about it, the center is here, behind this object. So how do you even draw it? So it may not work out all the time so well. Okay? Because this is before the center, something like that. It may not work out well all the time, but it can still be useful to you. Okay, so I'm going to use the third color now. Okay, so this one, I'll probably use this color. Okay. This one. So this goes and hits, and now it will retrace, it will go back. Why is it so? That's obvious. You see, this is a normal, and at this point, where is the normal? The normal is the radius all the time. We're going to draw a line from the center, that's a radius. So anything, the ray that goes through the center is actually traveling one of the radii of the sphere. So that be, and when it hits here, then it will get reflected back. Because the normal and the incident ray are one and the same. There is no angle between the normal and the incident ray. The angle is 0. So then it will reflect back. So that's the third one. Okay. So the third point is ray that goes through the center, okay, is reflected back. Or retraces its path. Okay, so these are the three easy rays. You can take one of these two, and then you'll be able to find that point. Suppose if I take this point, okay, let's say, suppose I take this point, some point here, in the middle. then what would I do? I will draw a line parallel to that, and obviously the parallel line that will go to the focal point. See, it's going to be like this, right? And what can I do? I can draw a second line that may go through the focal point and travel parallel. You see, now this is where they meet, so that would be this position, something like that. Okay. I've not drawn it properly. Actually, that should be somewhere here. Okay, so they should meet here, just be straight line like that. Because I can't have, this point here and this point here, but you can understand what it is. So for all these points we draw, then they will all lie here along this. So, okay. And what about this? What about this? This point, the bottom. Okay, the line that goes there, it travels along the axis, will get reflected back, right? So that will get reflected back. 1. Okay, and what else can I do from this point? I can draw any other line, for example like this, then that will get reflected back like that, and I will meet here. So this reflection and another ray that gets reflected here will meet here. Okay. This is generally not talked about, this point. We just say, just draw a line, vertical line. But this is what's actually happening. This point will make its image here, and this point will make its image here, and this point will make its image somewhere here. So it's now, okay. I didn't draw it to scale, the angles, thing, but it will be something like that. So the image, this object, and this is the image that you make. Okay, or any other line will get reflected as per the law of reflection. For example, if you take this one, it's here, the pole, it hits the pole, so it makes an angle theta, and then it will get reflected back the same angle theta. So that can also happen. Okay, so that is how you find points. So you can take any two rays. There is no hard and fast rule that you should be taking only parallel line and this line, that line. No. Okay, you can take any two rays. I can take two rays like this. Okay, like that, coming here, and maybe another ray, and then coming there. Any two rays. But after reflection, they will go and meet at this point. The rays will meet at this point. Same, any two rays, obey the law of reflection. But why I am not using this? Why am I using these? Is because if I use these, I don't have to use too much of the protractor. I don't have to measure the angles too much. Okay, I know the focal point, draw a parallel line, goes there. I know. And if I draw a line through the focal point, I have to go parallel. They're done. I don't need a protractor for that. Okay, not in a true sense, right? Okay, and then like if I draw a line through the center, then it's going to go retrace the path. Enough. Two rays are enough to find the point of intersection, and I know all the other rays from this point will have to go through that point. So I'm done. I'm good. Okay, so these are the laws. Keep this in mind.